logarithms, what are they? Well, they are a reverse of our exponential functions. The answer to a logarithm is the power. What power does this? Now, logarithms were created to depict either very, very small numbers in a slightly better, different way, or very, very large numbers. So they were kind of used to kind of condense things that could be written better using powers. So first, we just need to figure out what the heck they are. So it's really important that you know that an exponential is the opposite of a logarithm and vice versa. So let's kind of break it apart. We have some number, and it is a base b to a power of p. Now remember, our number is positive because our base is positive. Okay, so let's talk about this notation. This says, you read this as log base b. And we say the log base b of some number equals a power. What power would I put on the base to get this number? I think that's a better way to put it. What power would I put on this base to get this number? And we can see this here. We can take exponentials and rewrite them as logarithms. We can take logarithms and rewrite them as exponentials. It depends upon what we're trying to accomplish. Our calculator is limited to two types of logarithms. If you take a look on like the red calculators I have in the back, there's that natural log button. That is a log base E button. That LN button stands for natural log. Why they made it LN, I don't know, but that's just the abbreviation. And then if it just says log, that is a log base 10. It's called the common log. So those buttons are very limited. So much of this you won't be able to use a calculator for. You have to use your brain. You can do some things on the calculator, but most of the time you have to simplify using kind of logic. So let me show you how they work. First, let's practice going back and forth between logarithmic notation and exponential notation. So if you take a look at our first one here, this is the base, this is the power, this is our number. So to rewrite it, we just say the number is our base to the power of p. So if you take a look at what we've got here, our number is our base to a power of p. So this is our base, this is our power, and this is the number that it's equal to when we put it back together. Now, if we do the same thing for b, this is our base. So we would say that's a log base 3 of 9 equals 2. The log base 3 of 9 equals 2 is how we would read that. The answer is the power. This is my number. So the number 9 is equal to a base of 3 with a power of 2. And when you rewrite it in an exponential form, it should make sense. It should be a true statement. So both of those are true. Square root of 6 is 6 to the 1/2 power. 9 is 3 to the 2nd power. So always remember, this is our base, this is our power. If we put those back together, we should get the number inside. So that's how you have to kind of interpret that. Now, we should be able to go from our logarithmic form to exponential, but back from exponential to logarithmic. So that's what example 2 is looking at. So here, our base is 2, our power is 3, and this is the number that it was equal to. So the number goes inside of our logarithm. It shows that little base there. And so we know the power of 3 equals a log base 2 of the number 8. And what that really is saying is, what number would I put on a base 2 to get the number 8? What power would I put on the base 2 to get the number 8? The 3rd power. And so that's how that should make sense. The answer to a logarithm is the power that you would use on that base to get the number inside. So here, our base is 5, our power is 2, and our answer is 25. So if we say that our power of 2 is the log base 5 of 25, what's that really saying? Well, that's saying, what power would I put on 5 to get 25? Oh, the answer is 2. I would put a power of 2. The answer to a logarithm is always the power. So let's do it one more time. Our base is 10. Our power is -4. Our number is 1 over 10,000. So I would get a power of -4 if I put on a log base 10. That's I would get 1 over 10,000 if I put 10 with a power of -4. Now, we don't write log base 10 like that. That is what's called a common log. So if you just see the word log without a little number sitting there, because our number system is a base 10 system, that is another way that you could write that very thing. And that's the only one you don't have to include that little number, is if it's a base 10. If it's a base 10, you can just write the word log. You don't have to write the 10. It's not incorrect to put the 10 on, but the only time we don't have to include it is if our base originally was a base 10 number, okay? Any questions about converting back and forth between logs and exponentials and vice versa? Okay, so the main key is the answer to a logarithm is the power. Now, when I look at this question, remember the answer they are looking for is the power. So you're really saying to yourself, what power would I put on a 4 to get 64? And that's your answer. But I'm going to rewrite it using exponential form to kind of show you how the answer is. So I hope you kind of go toward the fact that 4 times 4 times 4 is 64. So the answer is 3. But let me show you why the answer is 3, okay? So remember, the power is y, our base is 4, our number is 64. So the number 64 is y to a power of 4. Now we know how to solve that. Oh, I'm sorry. Yes, I said it was a power. I wonder why you guys were looking at me like I was crazy. So if you say, what power would you put on a 4 to get 64? 64 is 4 times 4 times 4. And 64 is 4 to the third. So there's our answer. Y has to equal 3. Sorry about that. I kind of flipped that around, didn't I? So the answer is a power. So you're really asking, when you see this, what power would I put on a 4 to get 64? And so the answer is 3. There's not a ton you can show me. You could show me this, or you could even say that 64 is 4/3, 4 to the third power. You can, that answers that question, okay? So you should be able to do a lot of this. It's kind of a logic, logically driven sort of exercise. Let's take a look at this one. Now, you'll notice that we have a fraction inside, but our base is 3. So remember, the answer we're looking for is the power. What power would I put on a 3 to get 1 over 27? To flip something that wasn't originally a fraction, that's a negative power. So I need a negative exponent. So what I like to do for these ones is I like to rewrite this as 3 cubed. So we can relate it to that number 3. 27 is 3 times 3 times 3, or 3 to the third power. And then show that to flip it back where it belongs, so it has a base of 3, I would use a negative exponent. So your y would equal -3. Because what power would I put on a 3 to flip it and make it a 27? Well, the negative flips it, and the 3 makes it the 27. Our answer is -3. So as I said earlier, the common log is a log base 10. There's technically a little magical little 10 right there. If you don't see it, you have to know that the base is a 10. And it's not a bad idea if you don't see a number there, to add in that little 10. So if you see notation, the log of x, that's the same as the log base 10 of x. So a base 10, you do not have to write that. Now, log base 10s were it's called the common log. It was the first log that was used, and it was used for more of an accounting purposes. Large numbers back in the day, people were writing those out by hand, and some clever guy said, hey, if I have 4 zeros, why can't I just call it a 4? And that's kind of where logarithms were born. And then they're used for lots of different scientific applications, business applications. The logarithms are a thing. So what's great about our number system is a base 10 system. We're kind of used to think of scientific notation. So if you look at this one and you see the log of 1,000, all you have to do is count the zeros. So it's wonderful because of the fact that this is technically a base 10 and this is a 10 to the third power. So if you say, what power do I put on a 10 to get 1,000? We know the answer is 3. What power do I put on a 10 to get 1,000,000? The answer is 6. Now, for decimals that have, now this only works if there's ones and it can't be any other number, but 0.001, that's 1 over 1,000. There's 3 decimal places. Remember back when we were learning place value, back when we were in elementary school, tenths, hundredths, thousandths. So what makes 1,000? 3. What makes it flip over? Negative. So it's -3. Think about when you learn scientific notation, that -3 was used if it was a decimal value and you needed to show that your decimal was 3 places to the left. So base 10 logs are really, really nice. They go with scientific notation. They go with our number system. They're quick and easy. If it is a number more than 10, you just get to count the zeros. If it is a decimal value, count the places. Now, that only works if that's a 1, if that's a 1, if that's a 1. If it's 2,000 or 7,000 or 8,000, you can't quite do exactly what we just did. Now, our calculator has a log button. It's a common log. It's the most commonly used log. So that's what a log button does. It's a base 10 log. So you can use a calculator without an issue on these. You just hit the log of 321. Now I know a log of 100 is 2 and the log of 1,000 is 3. And so my number is somewhere between 2 and 3. It's not something nice. That's why they say round it to a particular number of decimal places. So the answer to 4 decimal places, as they've said, is 2.5065. How could you check your work? Well, it's checkable. If you put 10 to a power of 2.5065, you'll get something really close to 321. So that's a check, because the answer to a logarithm is the power. What power would I put on a 10 to get 321? Just use this button. Use the log button. That's what the button is on that calculator. And I would check just to make sure your entering it into your calculator correctly. Did we have a question? Yes. It's this one right here. Yeah, so if it says log, that is a base 10 log. If it just says log, that is a base 10 log. Did you have a question? We good? Okay, let's do one more. Log of 123. Same thing, you would hit log 123. You can't hit the ln button. That's a natural log. That's not a base 10 log. And if you hit the log of 123, we should expect that it's something just a little more than 2 because 10 squared is 100. And so we get an answer of 2.0899. And how could you check? Well, 10 to a power of 2.0899 should be something super close to 123. So these are checkable. That button on the calculator is a base 10 button. Yes. So on our calculators, we have 2 buttons referring to logarithms. We have the log, which we learned is a base 10 log. We also have the natural log. Now, the natural log of x is the same as e to the y equals x. So it uses that 2.71828 number. And the reason this has to exist is because there's so many scientific applications that has an e in it. They created a natural log to undo that operation. And so for these ones, we are going to make sure to hit that LN button, okay? So if they say to evaluate the natural log of 500, this time you would hit that LN button. Remember, a natural log is really the same as a log base e. So that's just a shortcut way of writing the log base e is to write ln. It is customary so that they don't look like variables, that they don't mush with the x, to write it in cursive. I know a lot of you don't write cursive very often, but it is customary in mathematics, if you're handwriting ln, to not go like this, because that kind of looks like a 1n. So they do tend to write it in cursive. So if you want to try to write it in some way kind of like that, okay? But that's the way I'll write it. Okay, so if we put the natural log of 500 into our calculator and we take it out to 4 decimal places, you get 6.2146. Okay, and then this one you could check if you put e to that power, you should get approximately 500. Okay. Now, what's interesting about the second one, the natural log of negative 500, is there anything we could put, any power we could put on an e to turn it into a negative number? No, it doesn't work, right? So if you try to put this into your calculator, it will say domain error usually, is what it's going to say. So this one is no solution. Inside of a logarithm, we can only, any kind of logarithm, whether it's log base 10, log base e, log base 7, log base 4, that number right there always has to be a positive. So if we try to enter in a negative, it is going to go, what? It's going to be confused. Now, what I wanted to show you here, remember how we had like the log of a million, we just got to count the 6 zeros, our answer was 6. Well, what's really cool is if an e is inside of a natural log, they are inverses of one another. The answer is just 5. Now, you can still put that into a calculator. You would hit the natural log button. You would hit second, and then the e would pop in there. You would put a 5. You would end the parenthesis. You would get an answer of 5. Okay, so that's how you use the natural log button. It's very essential that you only use those buttons in relationship to a log base 10 or a log base e. Otherwise, those buttons, unless you have some other type of formula, those buttons aren't going to get you anywhere. Okay, so that is some stuff about a natural log. Natural logs aren't that bad. They're pretty nice. Log base 10s aren't that bad. Evaluating, you should always think, what power could I put on the base to get that? What power could I put on the base to get that? That is your main goal as you go through this. What power would you put on that base to get that? Okay. And then this is your 6-3. So I'm going to do, see how here we have those there. I am going to do that first column. So I want to do one of each section real quick before we say goodbye for this video, okay? So it says for number 6 to rewrite that in exponential form. So for number 6, this is our base, this is our power, this is our number. So our number is going to be our base to whatever particular power that happens to be. So all they want you to do is rewrite this as Q equals 4 to a power of m. That's it. You're done. You're not evaluating anything. You're just rewriting it in exponential form. But 16, we're going the opposite way. So we have to rewrite this as the power is the log base b of our number. Okay. So here is our base. Our base is 4. Our power is x. Our number is y. So just rewrite it and put them where they go. The answer is our power. Our base goes next to the log, and our number goes inside. So that's all they want for the first two sections. Section 6, 7, 8, and 9, rewrite it as an exponential. 16 through 19, write it as a logarithm. So this is your answers for there. No evaluation involved, just do a flip-flop, because that flip-flop is going to be important as we do exponential and logarithmic equations. Now, 26 through 29 says to solve for x, converting the logarithmic equation to exponential form. So we're going to use what we did in the very first problem to answer this question. This is our base, this is our power, this is our number. So the number x is a base 3 to a power of 2. So what's x? Well, x is 3 squared, 3 times 3. So x is 9. So each one of those, when you do that conversion into exponential form, it should reveal the answer to you. So that's all you're doing for that section. That answer would be 9. What if I put a base 3 with a power of 2? What do I get? I get 9. Now, for 36 through 39, you're using either a base 10 or a base e. Okay, so we're going to do, I want to do the weirder ones. So let's do 37 and 39. For 37, if we do not see a base, remember that's a base 10. And when you have a power of 10, or I'm sorry, a base of 10 and a log in the power, they cancel out. And so the answer is just 32. The same thing happens in 39. Since the e and the natural log are opposites, if you have a base and you have a natural log in the power, the answer is just 1.06. And then 36 and 38, those are common logs. Use a base 10. If I have a power of 10, what would I have? Okay. Now we're going to keep going. We're going to do 42, 46, and 54, and then you'll have the rest of the time. You should be able to finish this right now. You saw how quickly I'm going through these problems. Yes. Yeah. So we'll do 3 more, and then you'll have the rest of class to work on these, okay? And most of these homeworks, they are just a process of kind of practicing quickly. Everybody got those ones now? Okay. So now let's do 42, 46, and 54. Let's do 42. This one I think was in our notes. What power do I put on a 3 to get 1 over 27? Well, I need a negative to flip it. And since 27 is 3 cubed, I need a 3 to turn that 3 into a 27. So the answer is negative 3. 46. It's a common log. There's really a base 10 there. What power do I put on a 10 to get 10,000? Great, count the zeros. The answer is 4. Okay, so those are wonderful. Those ones should be relatively quick. And then for 54, 55, 56, 50 through 58, you're just using the correct calculator button. So let's do 54 and 55. For 54, you are using the log button. It has to be that base 10 common log button. So on my red calculators in the back, just find the one that says log on the left side. And you're just going to round it to the nearest thousandth, which is 3 places. 1,000 has 3 zeros, so 1,000, 3 places. And I get an answer of negative 1.398 to the nearest thousandth. But 55, don't use the log button. Use the ln, the natural log button. So the natural log of 15 is 2.7081. Okay, so these should be quick and easy. Don't overthink them. It's easy to overthink these. And, you know, we're going to keep going throughout chapter 6 the rest of this week. So work on these now, because don't waste time, because you're going to have a lot of assignments due by Saturday. Okay.